So, welcome back, everybody. It has been a long summer for all of us, and I hope you enjoyed your free time or your first live conferences. We are happy to restart our Atto Fridays, and we are going to have a hot topic section with early career researchers, and they are going to tell us about, as the name says, some really hot topics. And we're going to move to our next speaker, who is from Jena, Karl Ziems. Here we try to pronounce everybody's name properly, you know. And luckily for you, I am German by proxy. So it's something that we can do. And he is going to talk about something that is much more chemistry oriented. So he's going first to argue why the time-dependent Schrödinger equation is hot and has been hot for a long time. And he is going to talk about correlation effects and their imprint in XUV ionization assessed by quantum model system. And the key issue here is that he wants to provide a systematic study of attosecond XUV induced single ionization dynamics in molecules by solving the time-dependent Schrödinger equation of a quantum model system composed of two different bound electrons and a nucleus numerically. And the system is driven by electron-electron and nuclear-electron correlation. And he's going to look at ionization dynamics beyond the single active electron picture. So, and the justification to say this time-dependent Schrödinger equation is hot. And it is hot since 1925. And I think if one day it stops being hot, we are going to be out of business, right?
Yeah.
And Karl studied theoretical chemistry in Germany, Jena, and England, Oxford. And he did research stays in computational chemistry and computational physics. And he's combining tools and models from theoretical physics and chemistry to understand fundamental processes for attochemistry. And he's hoping that he will excite the interdisciplinary community of the Atto Fridays about the theory of fundamental processes and show how solving the Schrödinger equation is still a hot topic, right? And hot it is.
Excellent.
So please feel free to start. The floor is yours. We're looking forward to your talk.
Thank you very much for the kind and thorough introduction. And also thank you for giving me the chance to present my research here in this really great seminar series. Yeah, so I have quite a lengthy title, which has quite some buzzwords in it, which I'm going to address now quickly in a little introduction. And I'm going to show our recent results. Yeah, my little cheeky reasoning why the topic is hot is solving the Schrödinger equation. Due to time constraint, I'm actually not going to talk much about how I do it, but I'm just going to show you mainly some results. But I'm always happy to talk with anyone afterwards or reading the papers. Okay, so let's talk about XUV ionization. And one could think of XUV ionization as an instantaneous single particle effect that kind of promotes an electron from the bound state to the continuum. Oh, I need a pointer. Here you go. And yeah, so we have our bound state, we have some kind of XUV pulse, and if the pulse energy is larger than the ionization potential, we will create a photoelectron in the continuum with this given energy. But of course, this concept or this explanation is a quite crude way. And lucky enough, we have the field of attosecond science who is tackling exactly this problem in much more detailed ways and thinks about time delays, whole migration, recently entanglement, and correlation dynamics that all go beyond this very simple picture of XUV ionization. And I want to talk about correlation dynamics today. And for that, we have to think about first, well, what is correlation and when does it become important? And well, it becomes important when we have more than one electron or more than one particle we are describing. And so if you want to describe this correlation as exact as possible, or let's say very well, we need to kind of implicitly have all the Coulomb interaction between the particles during our whole dynamics. And this has been done before, most famously for atoms, the helium atom. And we all probably know this very famous experiment by Osiander and co-workers who did helium, and they used helium and they ionized it with an XUV pulse. And then exactly this happens, what I showed before in this little comic, that one electron is promoted to the continuum, and we have the ground state of the helium plus behind at the parent ion, and we have our photoelectron with a given simple energy conservation rule. But they also showed that you can have a second pathway, which is defined by electron correlation, which means that our parent ion, the helium plus, is not left behind in the ground state, but rather in an excited state, here the 2s1, 2p1, due to the electron correlation between the two electrons present, which also leads to the photoelectron then having a lower photoelectron energy. And this work has been extended as well here in the group of Misha Ivanov, where they differentiated the electron correlation during these ionization processes into time regimes. First of all, the shake-up regime, which also has been seen in this experiment, which is quasi-instantaneous during the laser pulse interaction, and then also a longer-lasting regime of knocks, which are on the timescale of hundreds of attoseconds, even after the pulse interaction, but all lead basically to the fact that the parent ion leaves our system in more than just the ground state. So with this knowledge about atoms, our idea was to think about what happens in molecules. And in some way, molecules are very much like atoms, and in some ways, they very much aren't. And of course, in molecules, we will also have electron-electron correlation, as we have seen maybe in helium, but also molecules have an asymmetric structure in multicentric electrons. The electrons are not all like at one nuclei. And also we have several nuclei, and the nuclei can move in specific modes, and these can couple to our electron dimension as well. So the questions we are asking is, for example, can we still apply these ideas we had from atoms to molecules, and what might be new effects due to the nature of molecules? So, which brings me to the last point of model systems. So the reason we're using model system is that it's kind of not trivial if we now want to think about electron-electron and electron-nuclear correlation. And if you want to have it explicitly during the whole dynamics, we need to describe all these particle equal theory footage, and we want to do it quite accurate by solving the Schrödinger equation. And we can't do this with a real molecule, so we're using this model system, which is shown here, and I hope to explain quickly. Basically, our model system consists of 5 particles, and they all live in 1D, which was already nicely explained by the speaker before. And so we have a one-dimensional model system, and the 2 outer nuclei are just the boundaries of our molecule. They are fixed, they are point charges in our potential. The inner 3 particles, however, are all one dimension of our wave function. So we have a 3-dimensional problem, and they all can move in 1D 3 times, so I have a 3D wave function, and they all have explicit Coulomb interaction, which leads us with this potential operator where we have electron-nuclear interaction terms, electron-electron interaction terms, and we do all this with soft Coulomb interactions, just as Eloise did as well. So basically, if you now look at our model system, we have definitely electron-electron correlation because we have 2 electron degrees of freedom. It's an asymmetric structure where our electrons are multicentric, and we have a nuclear dimension, which we also describe quantum mechanically. So we also have electron-nuclear correlation, all on the same level of theory and solving the time-dependent Schrödinger equation. So the only thing that's now missing is a laser pulse, and we add the laser pulse in the velocity gauge as the vector potential. And then we can describe ionization. But before we do that, we have to kind of classify our model system in very nice terms that we know from computational chemistry, which is in terms of potential curves. So basically, we can solve our electronic time-dependent Schrödinger equation and obtain our potential curves in our electronic eigenstates. And here in the lower half, I show the potential curves of our model with 2 electrons in the nucleus. And up there, these are the potential curves of our parent ion. So we have only 1 electron left. And so basically, coming back to the helium example we've seen before, this is the potential curves of our helium, so our target molecule, and this would be like the helium plus they saw in the experiment, now just for molecules, so we have a target molecule and our parent ion molecule. And if you look at the wave functions of our parent ion states, we already see the multicentric version of molecules, because depending on which state we will end up, or depending on which state our parent ion will end up after the ionization process, the electron will be in different positions in space. So the first and the second state will be the electron will be on the left-hand side, just like this comic illustrates, whereas the second excited state will lead our molecule, our electron in the parent ion on the right-hand side. This will become important in a second. Okay, so now we know our model system and that we have potential curves. We know them from chemistry. And now we want to do actual dynamics. So what we are doing is we initialize our system, our wave function, first by calculating and by using a product of our electronic ground state, this one here, and our nuclear wave packet in the equilibrium position in this well here. And then we let our laser pulse interact with the system. And what I want to look at first now, first is the electron-electron correlation. And if we see the same trends as we know them from the atoms. So I'm focusing first on our electron, the parent ion system, and our photoelectron. And I'm going to investigate the parent ion by looking at which states are basically, which parent ion states are populated by this electron. And that's done by simple projection of our parent ion eigenbasis on our total wave function. And the photoelectron, I'm going to look at by collecting my photoelectron at the grid boundaries, or experimentally speaking, at a detector. And if I do this, this is one of the first things I see, for example. So here, as I said, I see time dependent now the population of our parent ion states, and I see that with a laser pulse centered around 0, I see population of our parent ion electron in its ground state, and the correlated event to that in the detector is to see a 5 electron volt photoelectron. So this would be my simple one single active electron picture. I remove 1 electron, and my parent ion is in its ground state. But we have electron correlation, so we can also have we can also end up in the first excited state of our parent ion electron, which results in the photoelectron having less energy. And the same, then we can end up with our parent ion in the second excited state. And again, in the spectrum, we would see our photoelectron, the correlated photoelectron, having a lower energy. So this is basically how we've seen it already from atoms, that we go beyond just populating, removing an electron and seeing the ground state populated, but we see that we have population of excited parent ion states. And these populations happen actually on different time scales, just as we've seen in atoms. So we will have shake processes very quick, and knock processes which are slightly longer in time. But I'm not going to go into detail here now. I would refer to publications here, and I would rather focus on a new effect that we don't see in atoms. And this is seen here in the photoelectron spectrum, because you might have already seen that there are always 2 lines. So I have a solid line in the photoelectron spectrum and have a dashed line. And this corresponds to my photoelectron spectrum in the forward direction, so having a detector basically here, and my photoelectron in backward direction, having a detector here. And we see quite clearly that there's a difference between the photoelectron which comes forward or backward direction. And that's something which doesn't happen if I do this in an atomic system. That seems to be a molecular effect. And one could not just say, well, this is due to the fact that our electrons are multicentric and we have electron correlation. This will lead quantum mechanically to this forward-backward asymmetry. But theoreticians or scientists like simple model explanations. And that's what, again, we did in this publication, which I'm just going to quickly reason for this NA0 peak. So one can intuitively understand this asymmetry by saying, okay, if I have a photoelectron of 5 electron volts, this means my parent ion, my correlate parent ion, will be in the state NA0. So meaning this is the state, meaning my parent ion electron is on the left-hand side. So we see it's like here. This means to create the state, this electron must have kind of left the molecular system. And this is inherently favored in forward direction, where it can basically just leave the molecular system, versus the backward direction, where it has an additional repulsive interaction when it wants to transverse the orbit of the other electron. So this is, let's say, the intuitive classical picture. If you're more interested in quantum analysis, I can read the paper. But basically, this can be done for each of these peaks and can be related to these various timescales of the shake and lock processes. Yeah, so basically, as I said before, when you go to molecules and we think about electron-electron correlation, we have the same effects we know already, like shake and lock processes and the population of higher excited states. But we also have additionally this electron correlation imprint due to the multicentric nature of electrons, which leads to this forward-backward asymmetry in our spectrum. So I've now talked about the electron-electron correlation. Next, I would like to talk about the nuclear-electron correlation. And I would like to start by thinking about in what system our molecule would be after ionization. So basically, as we've seen before, we will have a photoelectron, and we will have a superposition of electronic states in our parent ion. That's what we talked about so far. But obviously, I also have a nuclear degree of freedom in my model system, meaning I will also have nuclear wave packets, and each of these nuclear wave packets will evolve on each of the states that are in the electronic wave packet that constitutes our parent ion. So one can think of it like this. The picture here, we know the attosecond pulse will result in electronic population of one electron states of 0, 1, and 2. We know this here. And so we will have nuclear wave packets in all 0 of these states, and each of them will evolve independently depending on the gradient, which is defined by the potential curves. And we already know that, and we already know that this will happen on much larger timescales than the electron dynamics that's initiated by the XUV pulse. What's interesting in this system, which is very common for molecules, is that at some point we will have crossings of electronic states at some point along the potential curve. This is here the case here. This means if my nuclear wave packet would come close during longer timescales, would come close to this crossing point, what will happen is that we have electron-nuclear correlation, and we will have a non-adiabatic transition, resulting into a change in the electronic state population. Nuclear wave would go here, and it will distribute between these two states. And if we do the calculations on our Schrödinger equations, we will see basically exactly this, that on a longer time scale here of around 20 femtoseconds rather than 2 femtoseconds, we will see that at 17 femtoseconds, the NS2 state gets depopulated, the same way like the NS1 state gets populated. And this is exactly because the nuclear wave packet runs in this avoided crossing, which leads to a non-adiabatic transition. So this is known quantum chemists dealing with that because these kind of crossings are everywhere in nature or in big molecules. the question is now, what if we wouldn't initiate our system before the ionization in the equilibrium, but rather in a non-equilibrium state? Like shown here, let's say we initiated left of the equilibrium. And if we now say, we let this nuclear wave packet relax to the equilibrium position, and we would then ionize the system, as shown here. So basically we start the nuclear wave packet in a non-equilibrium position. It relaxes to the equilibrium. When it passes the equilibrium, it will have maximum momentum. And if we now ionize our whole system, what will change? And we're monitoring our non-adiabatic transition again, and we will see that now the non-adiabatic transition happens much earlier. And we could turn this game around and say, oh, we start the right-hand side of the equilibrium position, do the same again. Nuclear wave packet relaxes, passes through the equilibrium, will have a maximum of negative momentum, and then our XUV pulse hits our system. And then our non-adiabatic transition will happen much later. And this is a very intuitive idea here, just shown quantum mechanically, that our nuclear momentum will be conserved during the ionization between the target and the parent ion. So whatever momentum our nucleus in the target has, this momentum will also be conserved in our parent ion after ionization and will alter our non-adiabatic transitions, or in this case, what the relaxation dynamics of the nuclei on the various electronic states. And that is obvious a molecular effect. But when you're talking about starting a non-equilibrium position with our nuclear wave packet prior to ionization, there are obviously several effects that will happen, not just that the nuclear momentum, that the nucleus will have momentum at time of ionization, but we will also have effects like deformation of our nuclear wave packet, or we will have the fact that our nucleus will be moving throughout the ionization process. And we have now seen that this will lead to a nuclear momentum conservation, which will influence the electron-nuclear correlation on the long time scales in terms of non-adiabatic transitions. The question now is, does it also influence how the parent ion states are populated in the first place? So will this change in the nucleus, or in these three effects, will this lead to some changes in how the electronic wave packet in the parent ion behaves? So we are now thinking again about the short time scale. And the simple answer is it won't really. So the influence are rather small. So this is what we've seen before, how the parent ion states get populated during the laser pulse interaction. Here we see it now for the different, if it's been starting from a non-equilibrium position or not. And we see basically that the solid, dashed, and dotted lines kind of coincide. And the major difference is basically here. And when we see a difference in how much the NS2 state is populated, and one can dissect all these three effects with the publication and can see that this is basically due to the deformation of our nuclear wave packet, because it's here, this is a quite anharmonic potential. So it will lead to deformation of the nuclear wave packet, and this will change the resonance in the continuum and lead to this slight difference in how our electronic wave packet in the parent ion gets created. But overall, these are small effects, and one could thus say that the nuclear degree of freedom does not significantly influence the attosecond parent ion population. So if you're just interested in which state make up my my electronic wave packet in the parent ion, then the nuclear degree of freedom has not a big influence on that. So one could think about approximated theories, and we've done this in its latest paper. And of course, I think that's kind of interesting, at least if you think about whole migrations, where you're basically interested in how is my electron wave packet in the nucleus looking like. Okay, so almost done. I've talked now lengthy about electron-electron correlation, so with photoelectron parent ion, and now also explain nuclear electron correlation between our nucleus and the parent ion electron on the short time scale of the attosecond population and the longer time scale of these non-adiabatic transitions. But I always say, well, that's a photoelectron, that's a parent ion. I'm solving the Schrödinger equation. So I can't really say that's photoelectron, that's parent ion electron. My electrons are indistinguishable. I just give them the labels because that's much easier for the human brain to think about. But it doesn't really matter if in my simulation, my code, I collect the X or the Y electron at the grid boundary. So if I project the parent ion state on the X or the Y electron, doesn't matter, they're indistinguishable. So this also means, and that's the last point basically. So I've shown this figure now a few times. If we have our nuclear wave packet before any ionization, and if we displace it to a non-equilibrium position, the nuclear wave packet will react and oscillate, for example, in this well. It will gain momentum and do this pendulum behavior motion. And our electrons will react accordingly to this. So that's what I'm showing here. And it doesn't really matter which electron, they act the same way. It's just a way of of us thinking about it. So I can build basic density and look up at the momentum of our electrons. And I see that basically they kind of mimic what's happening in the nucleus. So basically that means we have a coupled electron nuclear dynamics in our bound states here. Just without any laser pulse, just boring laser-free propagations. We see if we start non-equilibrium, our nucleus will move and our electrons will move along as well. And the interesting part is now, what happens if we now ionize our system, but not just when it's in the equilibrium, as we've done so far, but if we do this several hundreds times, in this case, we start here, and every 1 femtosecond when we've started our nuclear wave packet and have our electron response, we now probe this basically by ionization. Every 1 second, we record everything I talked about before. We do it again, record our photoelectron spectrum, our populations, and see if there's any change. That's basically what we're doing. And if we do this and look at the observable of the photoelectron spectrum, we will see how we have an imprint of our coupled electron dynamics that happened prior to the ionization. We will have this as an imprint in the photoelectron that we can collect in our detectors. Or more specifically, we build the integrated photoelectron asymmetry. So not state resolved like for the electron correlation part, but just integrating the whole photoelectron spectrum in forward and backward direction. And you will see that we have an additional asymmetry on top of the asymmetry we know from electron correlation, which basically mimics our coupled electron nuclear dynamics we've seen before. So the reasoning is basically our nuclear wave packet is non-equilibrium, it will gain momentum, both of our electrons react to it, they are fully correlated, and if you then measure the photoelectron, it will have this information still imprinted. So yeah, that's our last molecular effect, basically, where we've seen that on top of the electron correlation asymmetry in the photoelectron, we will also see that we have an imprint of the coupled electron nuclear dynamics in our bound state that happened prior to the ionization. So that's it. That's the summary. So we did a proof of principle study of just thinking if we have all the various correlation effects that can happen in a molecule and ionize it, what could happen? Do our atomic effects still apply, or do we have any new effects? And in terms of electron-electron correlation, we showed that we have the same concept like in atoms of shake and knock processes on different time scales, but that we also see, due to the multicentric nature of electrons in molecules, that we see an imprint of our electron correlation in terms of forward-backward asymmetry in our photoelectron spectrum and resolved for various parent ion channels. Then we went and thought about nuclear-electron correlation, and we've seen that the parent ion electron nuclear wave packet are correlated in terms of these non-adiabatic transitions, and that we see how the nuclear momentum is conserved throughout our ionization process. And we also saw that if one is just interested in the population of our electronic wave packet, we can, the nuclear degree of freedom is rather can be neglected in some instances, at least. And then we've looked at the whole three-particle system and its correlation, and we saw that we can have integrated forward-backward asymmetry in our spectrum, and this origins from the coupled electronuclear dynamics, which happens in the target. Yeah, so that's it. A lot of talk about correlation, and thank you for your attention. And I want to thank all the co-authors, and especially I want to thank Jakob Blumke, did his bachelor thesis with me, and another research project, and who contributed a lot to this project as well.
So thank you very much for your really interesting talk. And you did make the case very convincingly, I have to say, that the time-dependent Schrödinger equation is indeed hot. So are there questions, comments? While we are waiting, I'm going to make another announcement, namely that starting from 2 weeks from now, we have asked our speakers to put some bonus material that is only going to be shown live and is going to be removed when the talks go to YouTube. I mean, we do appreciate that we have quite a huge following for a channel that is essentially niche, but we feel also that it is important to support speakers, and therefore we would really ask you to make an effort to come live to the talks, because this is very important if you would like to keep Atto Fridays healthy and alive. And therefore, we'll keep on putting things on YouTube for the sake of being inclusive, and but we will ask for bonus material that we are going to deliberately remove. Okay? So are there any questions? You know, people are quiet. There is one, I think. Yep. So someone anonymous, thank you for a nice talk. What is the time scale difference between shake up down and knock up down processes?
Yes, so let me, oh, I shouldn't move, my computer is not the youngest one if I do this too quickly. So, I mean, okay, this won't work. It can be quite, so the shake up, like if I remember correctly in the experimental investigation, was 20 to 30 attoseconds. So the shake up is rather quick. The knock processes, so for example, in this work by Misha Ivanov here, it's on the time scale of several hundreds of attoseconds. So as you see here, for example, in the state number 5, it can take quite a long time after the laser pulse vanished. And the same we see also for our system, which should be, I have another slide. Yeah, so we have it as well. So let's see. So this we have it up to, well, not really a whole femtoseconds, but like 500 attoseconds it's possible in the molecular system. Of course, so the main difference here is, which one should stress, is that the work on the helium is a system that exists in nature. So if they say the knock is on the timescale of hundreds of attoseconds, that is probably that it can also happen in nature. I'm using a model system, so I can always just say with certainty about qualitative effects, not quantitative effects. So I can definitely say the knock will be on larger timescales if what I see in the model system is true also in a molecule on the quantitative effect, that it will be, well, 700 attoseconds. It can also be a bit less, more. It's just, I can just say qualitative effects. And the qualitative effect for molecules, the knock is basically in the range of how it can be seen in this helium atom, for example.
So Anonymous, this is okay with you? whoever you are.
Here I can see it.
Yeah. Then there is Tran Trung Lu, who is asking if you could elaborate on your calculation of photoelectron. I think photoelectron spectra, I guess, right?
Yes, I should have.
Okay.
I was originally thinking of talking more about numerics, but then it would have been another 25 minutes talk by itself. So let's see what we have. No, this is just the numerics. No.
Also,
okay.
the anonymous attendee would like to know how to numerically solve the time-dependent Schrödinger equation.
Okay,
so
perfect.
This is
so
you can reply to both.
Okay, so I mean the numerics is very straightforward standard stuff. So the Hamiltonian we solve here, rather educational slide. Split operator method for our Cartesian grid for our 3 dimensions. We get our electronic eigenstates with the relaxation method. So propagation in imaginary time. And yeah, I think that's the most important numerics-wise. Split operator, relaxation method, fast Fourier transform, and discretized times with the short time propagator. So yeah, nothing special here. And what we are using for the photoelectron is basically at the grid boundaries. I'm collecting so basically photoelectron is differentiated in space. So when a part of my wave function reaches grid boundary, it's collected. It's then projected on our parent ion. Well, it doesn't have to. I can project it on the parent ion states to have it ion channel resolved, but I don't have to. I can also just calculate the full photoelectron spectrum. But basically, I just collect everything that runs into the absorber and convert it to momentum space, and then to energy, and then I have a spectrum. All the formula, all the numeric procedure are in the publication. I maybe should have copied them in there. I'm sorry. But yeah, as said, there is nothing new in there algorithm-wise. It has all been done.
Okay, is that fine by you? Or if anybody would also like to talk to the speakers, or
yeah, that's another one. I just saw it, but that might not include recolliding electron.
Let me see.
Yeah, we have we have recolliding. Not sure. So I reckon if you're referring to what we know from mid-IR, we don't really have that. Like we have XUV ionization. We don't expect the electron to be driven back, if that's what you mean by recolliding. And of course, if you do IR stuff, strong field ionization, in that sense, you need to be sure your quiver radius is within your grid. But if you want to calculate a quiver radius for XUV ionization, not that it's necessarily useful, it would be within the grid. But yeah, I don't think we have. Yeah, okay. That.
Okay, so understood. Okay, so if you would like to talk to the speakers, but you are a bit too shy to be on YouTube, just hang in there. No, some people are. They don't want to have the questions all over the internet, you know. I don't care anymore. After the pandemic, somehow I lost my shame, but some people are. So just hang in there, because we are going to stop the live streaming right now. And we would like to use the opportunity to thank all the people watching on YouTube across the globe. Great to see you again. And I hope to see you on the 21st, when we're going to have another talk. And we'll stop the transmission. Take good care of yourselves. Stay safe. And hope to see you soon.
Bye.
Bye.